At this point, we're ready to start and use cross-coupled NOR gates to form the basis of a memory element. All right, so here's the circuit diagram that you see on this graphic. And notice you have the S going with Q bar and the R going with Q. All right, so that's the way you arrange this circuit. That's one way to remember it. Q goes with R, S goes with Q bar. All right, so the idea here is that we want to be able to change Q where it stores either a 0 or a 1. So I have Q showing here. Right now there's a 0, so Q bar naturally would be the inversion of that. Now I want to say technically that's not quite right, because we don't know for sure that Q and Q bar are going to be opposite of each other. It turns out that they are, but if you were, a purist, you wouldn't really name this Q bar. You might name it like QN for negated Q. And it's not necessarily true that Q and QN would be opposite of each other. But that's semantics and a technicality. So just think of it as Q and Q bar. All right, so notice what we can do here. If I click on this and I change S equal to 1, all right? So S equal to 1, I have a NOR gate, okay? So 1 ORed with anything is 1, and I hit the bubble, it would be a 0 on the output, okay? So this 0 feeds over to here, okay? And so then I have a 0 for R. Check out R. R is a 0. And I have a 0 coming from the output of the bottom NOR gate. So 0 ORed with anything is 0, but then I hit the bubble, and now that's a 1. So I have initiated the storage of a 1 by putting S equal to 1. Okay, well, it's not really a memory element unless I can take that signal away and Q persists as a 1. So notice what happens when I take this signal away. This hold line comes on, but let's think about what happened there. When I take the signal away, S is now 0, but 1 has been fed into the input of the bottom NOR gate. Okay, so that feedback signal is what gives us the way of having the memory persist, because 1 ORed with 0 is 1, hit the bubble, that's a 0. 0 comes across here, I have 0 ORed with 0, flip that, that's a 0, or flip that, it's a 1. So nothing changes when I remove S equal 1, okay? So I can play around with S, and it's never going to change because I'm only taking the action of setting the SR latch. Okay, so the next interesting thing to do would be to reset the latch. Okay, so resetting, I would initiate the R for reset. When I hit that button, notice what happens. Q flipped down to a 0. Let's think about why. 1 ORed with anything. Okay, remember that feedback path wasn't there before. 1 ORed with anything is 1. Hit the bubble, it's now a 0. All right, so then this feeds forward, or I'm sorry, feeds back. 0 ORed with 0 is 0, hit the bubble. Now that this line, Q bar, is a 1. And that persists through to the input of the top NOR gate. So because of this feedback, that feedback gives you the holding action. So if I reset this, okay, that 1 is still there. So 1 ORed with anything is 1, hit the bubble, that's a 0, and it persists at clearing the memory element. Okay, so that's the basics of how a latch works, an SR latch works. I think you need to play around with this. I think this is a good time to get to a whiteboard and play around with making sure you understand how that feedback path is what allows the memory element to persist. Now, the thing that we don't allow, they call it a forbidden state. I mean, it's not like you're going to get a traffic ticket or something if you set S and R at the same time. The problem is we don't want to use this state because it's not clear what would happen next if we removed them both at the same time. if we remove them both at the same time, well, one of them is probably going to beat the other, and there's going to be a race condition, and we don't exactly know what's going to happen if you do a set and a reset at the same time. It's not a great, it's not what you'd want to do. You don't try to set a memory element and clear it at the same time. So functionally, it doesn't make sense to do. And circuit-wise, it gives you unpredictable results. Okay, so that's the SR latch. And I also wanted to include in this section the S bar R bar latch. Okay, this works on the same principle. The only difference is we use NAND gates, cross-coupled NAND gates, and we change the interpretation. Okay, so setting means set it to 0. So that's why it's called S bar, because the affirmative action, like if you want to store a 1 here, what you need to do is set S bar equal to 0. Okay, so making this input, this S bar input a 0, that becomes a 1, and then I have this feedback signal that allows me to have that memory element persist if I take it back to a 1. Remember the sort of the resting, just remember this kind of state is when both S bar and R bar are both 1s. Okay, so at this point on the S bar R bar latch, I've shown you how you can set that, and it will persist if I remove the initiating set signal. Now let's try to reset it. So the difference is, to reset, I need to take 1 down to 0. The initiating action is, some people call it low true. All right, so you make it a 0. And now with the 0 there, that forces this output to a 0. There's a feedback path that then changes this Q bar to a 1. And then this path will hold this so that when I go back to a 1, the 0 persists. Okay, so you might ask, well, what's the point of an S bar R bar latch? I think the main point is that from here, you can use either an SR latch or an S bar R bar latch, but sort of the tradition has been to go with NAND gates, all right? And so you can do the next step. If you remember the overview unit we talked about, the next step is to make a data latch, where we're not actually doing S bar and R bar. We're just saying, oh, I want to remember this data. And so here's the data. I'll either enable the remember signal or I won't enable the remember signal. And we use the memory element that way. So this is on the road to getting to a D latch. All right, so that's the 2 building block parts that we need. We'll move on next to the D latch.